We introduced the concept of friction on Thursday. We talked about two kinds of friction, kinetic friction and another kind of friction called static friction, which we didn't talk about in a lot of detail, but we mentioned briefly. Kinetic friction, that first kind of friction, with a resistive force, as is static friction a resistive force, but kinetic friction, a resistive force that acts against an object that is already moving. So you got a box that's moving across the floor, it experiences friction. Well, that's going to be kinetic friction because that object is moving. Another name for kinetic friction? What else can we call it? Well, we call it dynamic friction. I sometimes call it sliding friction. That's just my name for it, sliding friction, because I think it helps describe what it is. If we have a car tire that's skidding on the road, leaving a skid mark on the pavement, it's sliding. That's kinetic friction. If we have a car coming to a stop because somebody's pumping the brakes, the wheels keep moving, the wheel isn't sliding against the road, and that's actually what we call static friction. There's an important difference there between kinetic friction and static friction, and as we talk about static friction more a little bit later today, you'll see what that difference is. Bottom line is, if we think of kinetic or dynamic friction as sliding friction, we're more likely to be able to distinguish what type of friction that it is that we're actually talking about. If an object is sliding or skidding, it's kinetic, or call it dynamic, whatever you want. If it's not skidding or sliding, then it's going to be the other kind of friction that we call static friction. Now, the equation for friction we learned on Friday says FKF, the force of kinetic friction. By the way, what do those little vertical lines on either side of FKF mean? Absolute value means that we got a vector here. There's a direction associated with it, but that direction isn't going to be given to us by the equation. We're going to have to find the direction some other way. That's okay. We did that last week when we were solving those multi-force problems. We figured out which way friction was acting. Okay, that's not a big deal. The absolute value of kinetic friction is equal to a constant that we call mu. It's a Greek letter. We remember that it's called mu because it kind of looks like an M and it kind of looks like a U. Kind of looks like a combination of an M and a U. So we call it mu. It's a Greek letter that means the coefficient of friction. The coefficient of kinetic friction. It's a measure essentially of how much these two surfaces stick together. The higher the value of the coefficient of kinetic friction, the more they stick together, the lower, the less they stick together. Rubber on pavement would have a coefficient of kinetic friction of about 0.8-ish. Rubber on ice would have a coefficient of kinetic friction of about 0.1. Usually, the coefficient of friction is between 0 and about 1, although it can go ahead and get a little bit higher than 1 as well. The higher the value, the more they stick together. The lower the value, the less they stick together. It's equal to, the force of kinetic friction is equal to that value of mu times Fn. What does Fn stand for? The normal force, not the net force. The normal net force is F net, or sometimes we just call it F. The normal force is the force of the floor, or whatever the surface is, pushing up at 90 degrees. Right now, the normal force is acting directly up at 90 degrees. Sometimes it's acting on an angle. Now, for all the problems that we do today, the normal force will be equal to the force of gravity. That's not always going to be the case. I'll point out when it's not the case, but for now, it's going to be equal to m times g. Now, I don't want to write that in, because down the road, it's not going to be mg, but in all the problems, as I say, that we do today, it's just going to be equal to m times g. All right. Let's do an example. Let's do example number 5 that's in your notes here. Example number 5 says, we got a 1,700 kilogram car and it's skidding on pavement. The coefficient of kinetic friction between the rubber and the tires is 0.80. We know that it should be kinetic friction, right? We know that it should be kinetic friction because the car is skidding. And skidding is the same thing as sliding. And if it's sliding, then we call it kinetic or dynamic friction. The other kind of friction, static friction, not a factor here. Okay, it's sliding, therefore it's kinetic friction. What's the force of kinetic friction acting on the car, and what's the acceleration of the car? I've got a mass here of 1,700 kilograms. We have a coefficient, I'm going to call it mu k, just to distinguish between the coefficient of kinetic friction and that other kind of static friction. 0.80. How many digits is that 0.80, by the way? Yeah, it's 2. The first 0 doesn't count, the last 0 does. We want to find the force of kinetic friction, and we want to find the acceleration. I'm going to say FF, or FKF, is equal to mu times the normal force. I'm going to start subbing my numbers in. I know what mu k is, it's 0.80, but I don't know what the normal force is. Anyone? On a flat horizontal surface that we're dealing with right now and for the rest of today, the normal force will balance gravity. Right now, you're sitting in your desk, gravity's pulling down on your desk, the normal force pushes up and balances it. If it didn't balance it, if gravity is bigger, then your desk and you would fall down. It would fall through the floor into the ground. Okay, if the normal force was bigger than gravity, you'd rise up into the air. Neither one of those are happening, so they must balance each other. Therefore, the normal force will be equal to gravity. M times G, 1,700 times 9.81 meters per second squared. Why did we drop the sign of the 9.81? Why did we just make it positive? Yep. Well, the normal force is going up, yes. That doesn't really matter here, though. Yeah, it's the absolute value sign around the normal force. So we don't really care, even though it is Parker going up, we don't really care which way the normal force is going. We just want the absolute value of that normal force. The normal force sometimes can actually point down. It's not in this case, but occasionally it can actually point down. You're on the top of a roller coaster loop upside down, that normal force is actually pointing down. But in a situation like this, we'd still make it a positive value, the absolute value. So we multiply 0.8 by 1,700 times 9.81. We get a value here of 13,341.6 newtons, which rounds to, we're going to round that to 2 digits, 1.3 times 10 to the 4 newtons. So what's the value of the force of kinetic friction? 1.3 times 10 to the 4 newtons. Now we also want to find the acceleration. How do you find the acceleration here? Listen, I'm going to let you know a secret here. Right now, the force is with you. You know the force. You have the force. It's 1.3 times 10 to the 4. Now it's time to do a little Jedi training. Learn what to do with the force. Say some people are born with the force. Some people develop the force. We just developed the force, 1.3 times 10 to the 4. Now we got to learn what to do with the force. Any ideas? Any of you guys natural Jedis know what to do with the force? Yeah? Yeah, you got it. We're going to say A is equal to F over M. Now, we calculated the magnitude of the force of friction. Technically, that's actually a negative value, right? If it's moving to the right, friction acts to the left, right? So when I sub it in here, I'm going to include the direction, negative 13,341.6 newtons, and divide that by the mass of 1,700 kilograms. When we divide 13,341.6, the unrounded number, by 1,700, we get a value of negative 7.8 meters per second squared. What's the negative mean? Context of this question, we get a negative acceleration, which means this car is, yeah, Luke, slowing down, which makes sense, right? Skidding on pavement, car's going to the right, friction's going to act to the left, which is going to cause the car to slow down. I'm going to have you guys take a look at 2 questions right now, specifically questions 2 and 3. Now, these questions are both a little bit trickier than the example that I just gave you, but I'm confident that you guys can handle these. In both of these, you're looking not for the force of friction, but the coefficient of friction. You're looking for mu. Let's see what you can do with those. Let's have a look at question number 1 up here. It says, a 100 kilogram object is moving at 20 meters per second, comes to a stop over a distance of 40. We want to know the coefficient of kinetic friction between the object and the ground. Mass here of 100 kilograms. We got a velocity here of 20 meters per second. What does that correspond to? Is that VI or VF? What is it? VI. It's 20 meters per second at the beginning of the problem. We're going to call that VI. Now, speed, velocity, we're going to call it velocity. We're just going to assume it's moving in a positive direction, whatever direction that is. So we'll call it velocity. Over a distance of 40 meters, I'm going to call it displacement, actually, because even though they don't give me the direction, I know the direction is in the same direction as the velocity, the positive direction. So I'll call it displacement. Is there anything else that we have here if we read between the lines? VF is what, Nick? Good. VF is 0 meters per second because it comes to a stop. We want to find the coefficient of kinetic friction. Now, the only equation that I know that has coefficient of kinetic friction in it is that equation that we learned on Thursday and the one that we reviewed here today. FKF is equal to mu times the normal force. Let's rearrange that. The coefficient of kinetic friction is kinetic friction force divided by the normal force. Now, I don't know what the the force of friction is. The normal force, I know what that is. I told you guys earlier that for us, for now at least, it's always going to be mass times gravity, 100 times 9.81. But what's the force of kinetic friction? Well, I'll tell you what. The net force is the sum of all the unbalanced forces. There is only one unbalanced force acting in this problem, and that's friction. So if I can find the net force, I found the force of friction, since there is only one force that contributes to the net force in this case. So I'm going to say FKF, or the net force, is equal to m times A. But I don't know what A is, so I have to find A another way as well. Let's, for this one, say VF squared is equal to VI squared plus 2AD. Let's rearrange this. VI goes over by subtracting. VF squared minus VI squared equals 2AD. Now let's solve for A by dividing by 2 times D. VF squared minus VI squared over 2 times D equals A, the acceleration. So let's say 0 squared minus 20 squared over 2 times 40. That gives me negative 400 over 80, which is negative 5.0 meters per second squared. So this object slows down at a rate of 5.0 meters per second squared. Now, if we multiply that by mass, 100 times negative 5, we get negative 500 newtons. Frictions, did I make a mistake here, Andrew? 20 squared is 400. 20 squared is 400. 400 divided by 80 is negative 5, I think. I think that's right. You guys have that? Didn't square it? Hi, Cal? You did A is equal to delta V over delta T? But let's finish this, and then we'll go back and take a look at your way, okay? So we got a force of negative 500 newtons here. It should be negative, right, because it's slowing down. But I'm going to sub it in here as a positive value because FKF, we want in this equation the absolute value. So 500 divided by 100 times 9.81, I believe gives me 0.51, and there are no units associated with that. 0.51, which seems reasonable. Amelia, did you get that value? No? So then no, you can't do it the other way. What did you do, though? You said A is equal to delta V over delta T. That's a valid equation. Except we don't have T, though. Where'd you get T? See, if you use V equals D over T, that's your problem. This is not a group A problem, right? This is accelerating. This is slowing down. And V is equal to D over T is a group A equation. No. Time can be transferred from X component to a Y component. Okay, but you cannot use V equals D over T unless it's a constant velocity. And this is slowing down, right? Clearly slowing down. It's going from 20 meters per second to 0 in over a distance of 40 meters. So it's slowing down. We cannot ever use V equals delta D over delta T when the object is slowing down or speeding up. Does that make sense? So there's your problem right there. Look at all these group B equations now. the vast majority of the equations that we've learned are group E equations. There's only the one that's group A, and group A just does not apply here. Okay, I'll leave number 3 with you for another couple minutes, see what you can do with that. All right, let's have a look at 3 now as well. 165-gram puck, hockey puck. 165 grams, by the way, is about the mass of an actual hockey puck. It varies a little bit. There's a range of about, I think it's about 10 grams that a hockey puck is allowed to be in and still be a regulation hockey puck. This is about a little bit more than a third of a pound. So a 165-gram hockey puck is hit on a frozen lake and starts moving with a velocity of 12 meters per second. 5 seconds later, the hockey puck is moving at 6 meters per second. What's the coefficient of kinetic friction between the puck and the ice? What's my mass here? Not 165 grams, rather it's not 1.65, 0.165. We're going to divide by 1,000, so 0.165 kilograms. Now we get a velocity here of 12 meters per second, and we have another velocity here of 6 meters per second. What's the first one? 12 meters per second. Is that VI or VF? Turns out VI or VF? VI, good. And VF is going to be 6 meters per second. We've got a time interval here of 5 seconds. And we're looking for the coefficient of kinetic friction. So we start with the same equation as we did last time. Rearrange it. Mu K is equal to force of kinetic friction divided by the normal force. We know the normal force, or we can find it easily, but kinetic friction, a little bit harder. For that, we're going to say, well, there's only one force acting here. It's friction. So the net force, MA, is provided by that friction force. Let's find the value of friction by saying M times A. But we don't know what A is. For this one, I think we're just going to have to say A is equal to delta V over delta T. Delta V is 6 minus 12 over a time interval of 5 seconds. Negative 7 divided by 5 gives me 1.4. Is it 1.4? 1.2? Yep. Yeah, it is. 6 minus 12 is negative 6, you're right. That's why I got 1.4, because 7 divided by 5 is 1.4, right? It should be 6 divided by 5, which is negative 1.2, right? Okay. So we get negative 1.2 for the acceleration. We're going to say my mass here is 0.165 times negative 1.2, negative 0.198 newtons, which now we take the absolute value of that, sub it in here, 0.198 newtons divided by the normal force, which is 0.165 times 9.81. Do that, we get a value of, let's just see here. We get a value of 0.12, 0.12, and there are no units associated with that, just 0.12. That should make sense, right? In the first one, we get 0.51. Here, we're talking about ice now. Coefficient of friction between this block, this puck, and ice is going to be quite a bit lower. Right? That varies, right? Depending upon the amount of snow on the ice, it varies the amount of friction. The fresher the ice is, the lower the coefficient of friction, right? The more snow is on the ice, the higher the coefficient of friction. Now, I alluded to static friction earlier on in class, but I want to spend a little bit more time dealing with it in a little bit more detail here now. We said kinetic friction is a force of friction that resists motion when an object is already moving. Static friction is that force of friction that tries to keep an object from beginning to move. It's not sliding friction. Clearly, if an object is not moving, it's not sliding. If an object is sliding, it's kinetic friction. If it's not sliding, well, then it's not moving. Then it's going to be static friction. Now, static friction has an equation that looks similar to but is not the same as the equation for kinetic friction. We're going to say FSF, force of static friction, maximum. There's the biggest difference right there. It's not just FKF, it's FSF max equals mu, mu being the coefficient of static friction with no units, times the normal force, which for today at least, the normal force will be equal to m times g. It's going to balance gravity out. Why do we say FSF max rather than FSF? Because the force of static friction is a variable force. It's a stubborn force. It's a pain in the butt force. Kinetic friction can sometimes give us trouble because it resists motion, but at least kinetic friction is what it is. If kinetic friction is 10 newtons, then kinetic friction will always be 10 newtons. If it's 30, then it's always going to be 30 newtons. Static friction, on the other hand, static friction is a variable force that pushes back as hard as we push until it reaches a maximum value. For instance, let's say the maximum force of static friction acting on this desk is calculated to be 50 newtons. That doesn't mean the force of static friction on the desk is 50. The maximum force using this equation is 50. But the actual force will simply be however hard I push until I exceed the maximum force. Let me give you some examples here, okay? Maximum force on the desk, 50 newtons, let's say. Let's say I push on it with a force of 10 newtons. Static friction isn't 50. Static friction is only 10, because static friction only pushes as hard as it needs to push to counter my force. So maximum force is 50. I push with 10, static friction is 10. I push with 20. How hard does static friction push now? 20. I push with 30. How much does static friction push? 30. I push with 40. How hard does it push? 40. I push with 49. How hard does static friction push? 49. If I push with 51, how hard does static friction push? 0. Static friction is now 0. Why is it 0? Because it's kinetic. I moved it. Right? If I push, static friction isn't necessarily 50. It's whatever I push with. But if I push with more than the maximum value, then it becomes kinetic, and there's 0 static friction. Then we'd have to calculate the value of kinetic friction. Yep. No, the maximum static friction is not equal to kinetic friction. Maximum static friction is equal to mu s times Fn, not mu k times Fn. The reality is here that the coefficient of static friction will be larger than the coefficient of kinetic friction, and therefore the maximum possible force of static friction will be higher than the force of kinetic friction. So again, I push with 30 newtons, static friction pushes with 30. I push with 40, static friction pushes with 40. I push with 49, static friction pushes with 49. Because remember, that stubborn force pushes as hard as it needs to push. But there comes a point when it gives up. Can't push any harder. And that's when I push with a force that's bigger than 50. I push with 51, static friction says, yeah, whatever. I can't keep up anymore. Okay, let's just let it go. Let it move, and now kinetic friction has to deal with it. Right? Now, kinetic friction would probably be something like 42. I push with 30, static friction is 30. Push with 40, static friction is 40. Push with 49, static friction is 49. Push with 51, static friction is 0, and kinetic friction might be 42. If I push with 100, kinetic friction is 42. If I push with 1,000, kinetic friction is 42. Kinetic friction is what it is. Static friction changes depending upon how hard I push until I beat it, until I exceed that maximum possible value, which in this example that I just gave you is 50 newtons. So, you see there in the paragraph below it says, static friction behaves differently than kinetic friction. in that it acts only as strong as it needs to act. That's what I was just talking about, right? I push with 30, it pushes with 30. I push with 40, it doesn't push with 41, it pushes with 40. I push with 49, it pushes with 49. It pushes only as strong as it needs to. It's always going to be equal to however hard I push, whatever the applied force is, until I reach a maximum value. Once I exceed the maximum value, then it's going to move. The maximum static friction is 50 in this example. I push with 51. All right, static friction can't keep up. It moves. Now I got kinetic friction. Now I got to calculate FKF using the equation that we learned on Thursday and the one that we reviewed earlier today. We touched on this earlier as well. Static friction in itself is not always greater than kinetic friction. In the example that I gave you, kinetic friction was 42. Static friction could have been 49. But static friction could have also been 30. Static friction in itself is not always bigger than kinetic friction, but the maximum possible value of static friction is always greater than kinetic friction. So kinetic friction in that example was 42. Static friction could have been whatever, depending on how hard I pushed, but the maximum static friction was 50, which is bigger than the kinetic friction. Let's do an example here now. Example number 6 in your notes says a 20-kilogram box is at rest on the floor being pushed to the right. There's a coefficient of static friction between the floor and the box at 0.6 and a coefficient of kinetic friction of 0.4. That makes sense. Kinetic friction is going to be smaller. What's the force of friction between the box and the floor if it's pushed with a force of 50, 100, 150, 200? Listen, we don't even know if it moves or not. How do we know what kind of friction it is if we don't know if it moves? Well, let's determine what kind of friction it is. Let's get up here SF max. That's equal to mu s times the normal force, which is 0.60 times 20 times 9.81. Multiply those three numbers together. We get a value of 117.72 newtons. That is not the answer to any of these questions. That's just how hard I can push before it starts moving. Does that make sense? Okay, the maximum value is 117. I push with 50. Does it move? No, because I haven't exceeded the maximum value. If I pushed with 200, then it would move. We'll deal with that when we get to it, though. Push with 50, doesn't move. 50 is less than 117.72, therefore doesn't move. Therefore, the force of static friction, not the maximum force of static friction, that's 117. The force of static friction that's acting in this particular case, it's just 50. It's however hard I push, remember? As long as I'm not exceeding the maximum value, static friction is going to be however hard I end up pushing. Now, if I push with a force of 100 newtons, does it move? No, does it move if I push with a force of 100? No. Okay, if it doesn't move, what kind of friction do I got, Dylan? Static friction, good. What's the value of static friction going to be in this case? And Mark, what's static friction going to be in this case if it doesn't move when I push with 100 newtons? 100 newtons. All right, I can push as high as 117 before it starts moving. I push with 50, doesn't move. 100 doesn't move. I can push with the 116, not going to move. I push with 150, does it move now? Jen, does it move now? Yeah, it does, because I've exceeded that, right? I've beat it. I've won. I've beat static friction. It moves. Well, what's the force of friction, 150? No, let's calculate the force of kinetic friction here. FKF is equal to mu k times the normal force, which is 0.40 times 20 times 9.81. 0.4 times 20 times 9.81 gives me a value of 78.48. or 78 newtons? If I push with 200 newtons, does it move? Luke, does that move? Yep. What's the force of friction here? It's kinetic, right, because it's moving. Ethan, what's the value of the force of kinetic friction, do you think? Brayden, do you know what the value of kinetic friction would be here? 78 newtons. Because remember, kinetic friction is what it is. If kinetic friction is 78, it's always going to be 78. What if I push with 1,000 newtons? Okay, not 200. I push with 1,000. Clearly, it's going to move, right? What's kinetic friction going to be when I push with 1,000 million? 78. I push with 1,000,000. Does it move? Of course it does. What's kinetic friction going to be? 78. Static friction increases as I push harder until I beat it. And then kinetic friction is what it is. Yep. Question, Parker? Yeah. Actually, technically, they'd all be negatives, right? Technically, they'd all be negatives. Really, I probably should have asked for the magnitude of the force of friction rather than the actual force of friction in this case. But yeah, you're right. Yeah. When you're not asked for the magnitude, it does include a direction, but that's not what I meant to get out of this. I just didn't word it very well. It's a good point, though. All right, I'd like you to have a look at your worksheet. Same worksheet. This time, question number 5, please. All right, let's have a look at number 5 now. It says 100-kilogram object is at rest on a horizontal surface. The coefficient of static friction is 0.6. Kinetic friction is 0.45. We push with 400 newtons for 5 seconds. What's the force of friction acting on the object? First, let me tell you this. The time interval here is completely irrelevant. If you're pushing on something and it doesn't move, it doesn't matter how long you push on that object for, it isn't going to move. Okay, if you push on it and you want it to move, don't push for longer. What do you got to do? Push harder. Apply a bigger force. The same force isn't working? Okay, don't keep wasting your time. It's never going to work. You got to push harder. So this time is irrelevant for all of these questions. Now, does 400 make it move? I don't know. Let's find F max to see if it moves here. Let's say it's the coefficient of static friction, which is 0.60 times the normal force, which is 100 times 981. That gives me 588.6 newtons. That's not static friction. When you calculate that value, that's never going to be static friction. That's how much static friction can be. How much is it? Well, in question A, you push with 400 newtons. Does it move? Andrew? No. Remember, static friction is that stubborn force. It pushes as hard as it needs to push. I push with 400. How hard does it need to push? 400. So then we're going to say the force of friction is static because it's not moving, and it's only going to push with 400 because it doesn't need to push any harder. Now, what if I push with 500? How big is static friction?
500.
500, because that's how hard it needs to be, right? It doesn't need to be any more than 500 if that's all I'm pushing with. If I push with 587, how much does static friction need to be? Doesn't need to be any bigger than 587 because that's what I'm pushing with. Just going to match whatever I do until I exceed the maximum value. Now, I'm pushing with 650 now. I win. I beat static friction. That stubborn, in-your-face static friction, I beat it. I pushed further than its maximum possible value of 588. All right, now it's kinetic friction then. If it's moving, it's kinetic friction. And if it's kinetic friction, I better find its value using the other equation, FKF, is equal to mu times the normal force. Now it's the coefficient of kinetic friction, which is 0.45, times the mass, which is 100 times 9.81. What do I get for FKF here? Who's got that? What is it? 441.45. We're going to round that to 2 digits. 4.4 times 10 to the 5 newtons. Now, look at this. Question A, I made 3 digits. Why? Because I only used one number. No, it's not 10 to the 5. What was it, 440? Times 10 to the 2 then, right? Thank you. That was 3 digits because I only used the one number that has 3 digits. But for this, I used a 2-digit number, a 3-digit number, and a 3-digit number. So here the final answer should be 2 digits. What happens if I push with 700 newtons? What's kinetic friction then? 4.4 times 10 to the 2. What if I push with 1,000 newtons? What if I push with 10,000 newtons? Friction will be 4.4 times 10 to the 2. Question C says, how much force is required for the object to start moving? How hard do I need to push to get it moving? Better? No, but I used the 0.45, right? For the coefficient of coefficient. Does that make sense? Yeah, that leading zero doesn't count there, right? No, I didn't use it for A. I calculated FSF max and got 588.6, but I didn't use that number, right? And my answer just depends upon that one 3-digit number. How much force is required to get it moving? No calculation required here at all. If I push with 500, does it move? Nope. Push with 550, does it move? Nope. Push with 587, does it move? Nope. So how much force is required to get it moving? Aoife? Yep. No. Yes. 588.6 was it? .9 times 10 to the 2 newtons. We're going to round this one to 2 digits because when we calculated that, we used the coefficient of friction, which was a 2-digit answer. So, no, I'd take that. I'd take it as is there. Listen, this was a little tricky for significant figures. If I gave you a question like this on a test, and probably a good chance that I will give you a question like this on a test, it wasn't my intention to kind of mess you up with the sig figs on this, with 3 digits, then 2 digits, then 2 digits. I'd probably put everything as like 3 digits or everything as 2 digits, just to make things a little bit easier there, okay? So don't lose too much sleep over that if the sig figs confuse you there. Yep. All right, I'd like you to take a look now at the rest of the worksheet. Okay, we've done questions 2, 3, and 5. I want you to do questions 1, 4, 6, and 7. 6 and 7 are just qualitative questions. It's 1 and 4 that are the mathematical-based questions. See what you can do with those here, please, at your desks and for homework tonight.